schedule. And the good news is that means we finished 15 minutes earlier than it says. So we're going to only have one session of intro talks during this session. We just were able to combine them. Yeah. Okay, thank you. So for this afternoon session, we start with Elaine Winston. She's going to talk about star formation in the outer galaxy.
Afternoon, everyone. So my name is Elaine Winston. I'm a postdoc here. I work with Joe Hora over in the OIR department. So yes, so we're going to be talking about star formation in the outer galaxy, and I put here that it's a Spitzer and Wise census of YSOs because I think most people so far have been talking a little bit further wavelengths, a little bit longer than what we're doing today. Okay, so why are we interested in the outer galaxy? So how do we find that star formation may differ from what we know in the inner galaxy? We usually study things like Orion or Gould's Belt, things that are relatively nearby. We know that the outer galaxy has an intermediate metallicity value between the inner and the galaxy and the Magellanic Clouds. So this is kind of our reason for looking in this direction, to see what's out there and to see if it in any way differs. How might it possibly differ? Well, we're interested in facts like, is the physical scale of these clusters, is it similar, is it different? Is the total membership affected? Is the star formation efficiency? Is the most massive star in the cluster of a similar mass, given its size scale, to what we might find in the LMC or in the inner galaxy? We're looking at the IMF, which we will actually discuss today, and then talking about the disk evolution, lifetimes, the initial masses, with it, of course, the ever-present link to planet formation and aliens. So our study, our first initial paper we have out now is on the SMOG field, which is just one small 21 square degree field towards the outer galaxy. And then we are now currently working on our SFOG or SFOG field. So that's going to be from about 60 to 270 in the anti-galactic center pointing. I can't say that word correctly. So what do we know about the outer galaxy? So metallicity declines with galactocentric radius. So actually, Huang et al. 2005 say basically it's dropping off towards about where the sun is, about 8 kiloparsecs, and then may in fact be kind of just leveling off towards the outer galaxy. And they suggest this may be like a different formation mechanism for the outer part of the galaxy towards the inner disk. The cosmic ray flux is lower in the outer galaxy. The average cloud temperatures are also lower and the crossing times are less frequent, so there may be fewer opportunities for clouds to combine and perhaps collapse. We know that star formation rate is affected by density, temperature, the chemical abundance of the gas, and also the presence of massive stars, and the metallicity may have an effect on that. So we want to then study how this affects the overall rate. So I just did in the bottom graph here. Oh, I forgot we have this. There we go. So this is the SMOG field, and this is the old GLIMPS. We have GLIMPS, GLIMPS 2, MIPS GAL studies around here. The GLIMPS 360 field is going to cover up here. So, there we go, sorry. So this is what we're going to use for SFOG. So the SMOG field is Spitzer mapping of the outer galaxy. This was carried out 2008. This was the cryogenic mission for Spitzer. So we have 4-band IRAC and MIPS 24 micron for this whole field. It's a 21 square degree field, 7x3 from about 102 to 110 in the outer galaxy. It crosses the Perseus and outer spiral arms, and they're at about roughly 2 to 6 kiloparsecs, so we're looking through those. So most of the star formation that we're seeing in this field is associated with one or either of those spiral arms. So just in kind of summation of we use the usual CMD selection methods, we get about 4,000, nearly 5,000 YSOs, or YSO candidates. Using the usual SED slope, we classify those. So we get around 1,000 class 1s, 3,000 class 2s, some class 3 objects which are not X-ray identified, so they're just weak class 2s to most extent, and possible transition disks from the MIPS data. So these plots just show all of the YSOs. There we go. Spatial distribution up here, separating just the class 1s, class 2s, so you can kind of begin to see some structure in these clusters popping out. And then the class 3s are a bit more widely distributed. So using DB scan, some density-based spatial clustering of applications with noise, very nice. Basically, it's this nice clustering technique that uses only two variables. So you have a minimum club size or minimum clustering size and a minimum separation length, essentially the density that you require in order to get a clump. So as the values up there, what we find 68 associations or clusters in this region. And here you see this is the 8 micron image grayscale, and we've just outlined we use convex holes to identify the kind of rough area of these clusters. So we put them up there. The line also, we also have some UKIDS data that we used in conjunction with 2MASS. So there's slightly more smaller clusters that pop up on this side because we have deeper UKIDS in the near infrared. Here. So yeah, we have 68 clusters and all of them have 8 or more members in this case. So we think that they're all reliable, and 8 of those have more than 80 members in them. So these are our big 8 clusters, just to briefly see that they're, various, there you go. Some very condensed regions. This one here is kind of our favorite. You can see that in some cases that, the convex hole that we're actually applying doesn't incorporate all of the members that are perhaps associated with this region, but it just gives a first approximation at least. You see some of them are a bit more extended, but all of interest, I think. So yeah, they all have a few hundred members. We don't have anything that's really got anything like close to 1,000. They're all just less than 500. One cluster, so we did an estimate of the total membership of the cluster just based on the masses of the objects from the SED fitting. And one does look like it has a few thousand members, at least. This would be above about 3 solar masses. Generally, they're pretty large clusters. They're kind of on the Orion scale for the most part, or at least Orion A and B. Not particularly high mass according to the SED fitting. There's just about 10 to 13 solar masses, the most massive objects in these clusters. And a range of distances. They're both associated with both of the spiral arms here. So, thanks. So again, this is a close-up to show you we have a nice color image, and again showing you that in this case, for instance, we have just a bar of class 2s forming, so it looks like a rather odd-shaped cluster, but in fact, obviously, we assume that there's a lot of class 3 membership out here. We have Chandra observations scheduled for next March now, hopefully, so we'll be able to identify those cluster members and get a bit of disk fraction, which will be interesting. We did subclustering with minimum spanning tree and also with the DB scan again, and did find basically all of the larger regions have many subclusters. The protostellar fractions do vary, but there's no real consistent, we can't really tell if there's any kind of evolution going along or triggering star formation in any of these clusters. We're hoping that once we get the X-ray data for some of these, we'll be able to talk about that further. So I guess our most interesting result would be the initial mass function. And the answer is it looks exactly like the inner galaxy, pretty much to the fit here. So there's no statistical difference to what we would expect. So that's good. We don't think that there's anything weird or wacky going on out there. But of course, this is just using the SED fitter robotized. So could all change. But so far, looks like star formation is continuing happily without any influence. Just as a comparison with WISE, to kind of compare what happens when you get the WISE data and have the IRAC data. As you see, we find 600 odd WISE YSOs in this region. And this plot is showing the IRAC YSOs, and the magenta colored outlines are the clusters identified using the IRAC data, and the gray are those identified by WISE. So WISE isn't finding as many of the YSOs, it's finding mostly the embedded, but it basically traced the same clusters. So if we're doing studies with just the WISE data, obviously it's all sky, so that might be better in some cases you don't have IRAC. It's basically finding most of the same regions, but just not all of the YSOs. So the SFOG field then, we're just working on that now, putting together the paper. This is using the GLIMPSE 360 survey data. It only has IRAC bands 1 and 2. So we're now using the WISE data in conjunction with all of this. This is going from about 65 to 270. I'm not sure if that really came out. I had to steal that from the Spitzer website. Yeah, it's really hasn't come out very well. Yeah, we basically, it's a very large field, so we couldn't create images of it. We're basically creating the images of the cluster right now that we've found. but it's about 180 degrees long. So far we found about 42,000 YSOs in the field, and if we add in SMOG, which is a bit of a gap, it's in here somewhere, we get about 47,000 YSOs in total in candidates. We then went back and did DB scan clustering and found 620 clusters in this region. Some of them we were finding like W3, W5, Q. And so you have W3, W5 and Cygnus are all in here. And about 100 of them were found with associated with YSH2 regions. And so again, we did SED fitting. And again, we find that it's consistent with the inner galaxy. This on the left here is those galaxies, or sorry, those clusters with greater than 10 solar mass objects, and those without in the blue. And then this is the inner galaxy versus the outer galaxy, so separated for clusters at 12 kiloparsecs from the galactic center. And in both cases, statistically, the slopes fit with what you would expect from the IMF. So just to conclude, we're now doing a large study from 90 to 70 degrees in the outer Milky Way. We've got over 45,000 YSO candidates, 620 clusters or associations. Everything looks very similar in the outer galaxy to the inner galaxy. So we need some better statistics and some extra X-ray data, and we'll hopefully have some more results in the near future. So thank you very much.
Questions? Okay. Yeah.
Quick question about your SMOG field. So you had two populations, basically at two different distances, passing through different spiral arms. Mm-hmm. Was there anything statistically significant between those two populations?
So it's kind of hard to tell because the distances are all from the YSH2 region. So we do get populations that do seem to be lying between the spiral arms based on the YSH2 distances, and they're from various kinematic studies. Some of them do have are based on spectroscopic distances, but they're for the more well-known regions and that are in the arms. But yeah, there do seem to be star formation going on between them. Yeah, between the spiral arms. But yeah, can't really say for sure. Thank you.
So what are the most massive stars you're finding?
So actually, we're not finding anything much more than so in the SMOG field, it's about 13 solar masses is the most massive object. In the whole SFOG field, if we're calling it for that, it's about 19 solar masses, and that's just one object. So there it doesn't seem to be very much. There's not much. So it could be seen as a sign of possibly, it's not quite like Orion and these multiple massive objects in these clusters. But unfortunately, this is again using the SED fitter. So we are planning to go back and essentially go into each of these clusters in more detail, the more interesting ones.
Sure, but you don't find a very luminous object.
No.
No,
we don't. So actually, when we do the SED fitter, we specifically we don't allow the distance to vary. We just use the YSH2 distances. If you do allow the distance to vary, it will give you something much more massive, obviously. But yeah. They're generally within about 10 to 20% according to the kinematic distances. So if you're talking about a few kiloparsecs, then perhaps the answer will be not vary, and that will have a great effect on the mass. So we're kind of hoping essentially in aggregate that the comparison is valid because we're using the one metric to identify all of these distances, so they could all be off by similar amount. But yeah, it's an issue.
Any last question?
And what's the next region?
It's about 16. It's about 16.5 kiloparsecs from the from the galactic center.
Okay, let's thank Ellen again. Now we have the introductory talk. So can all the speakers please line up here?
Yes.
Oh, yeah, sorry.
All right. Hi, everyone. My name's Mike Foley. I'm a grad student here at the CFA working with Alyssa Goodman and Lars Hernquist. And I just wanted to give a quick introduction to some things I've been looking at recently. So as I believe Alyssa mentioned at some point, I'm kind of interested in the intersection between turbulence and stellar feedback. And so we have this great spreadsheet that Alyssa and Joao started a couple of years ago. So if you work on feedback at all, I'd love to talk with you to try and fill in the spreadsheet from both the observational and simulation perspective. But now I'm looking a little bit more on how turbulence develops in regions that are relevant to star formation and stellar feedback. And a lot of this is motivated by a recent model that comes from the column density PDF. So, you know, if you have like isothermal turbulence, you'll get a log normal column density PDF. But in observations, there's this power law tail. And recently it's been suggested that the power law tail is actually indicative of the dense star-forming gas. And a recent model by Blakeslee, Burkhardt, and Phil Mox has shown that this turnoff between log normal and power law happens at right about what we would call the post-shock density, which is a density cutoff above which you get a little bit of the gas behind shocks and the shocked material. And so we really want to look at how turbulence is developing just behind shocks, because that may be the regions in which stars are actually forming. And so to do this, the first thing we've done is just look at a very idealized shock using Athena++. And up in the left, the shock is shown in the red. And what I've done on the right is I've just cut out basically the red part, and I'm computing the velocity structure function parallel and perpendicular to the shock. And if we were just looking at a normal turbulent box, we would expect the velocity structure function to be essentially the same in all directions, like isotropic. But we get something very different in the parallel and perpendicular directions here, potentially indicating that turbulence develops in an anisotropic way behind shocks. So if stars are forming there, it may mean stars see anisotropic turbulence, which could have implications for how we drive turbulence in our simulations of star formation. Thanks.
Hi, I'm Joe Hora. I just wanted to show some results that I have been working on with a local high school student during the past summer. We haven't talked too much about infrared dark clouds or IRDCs here, but of course these are the very dense clouds that are seen in silhouetted against the background of the Milky Way. And we wanted to search the large data set. I mean, there's been catalogs done of these before, but we wanted to search the new IRAC band 1 and 2 data sets that have become available over the last few years. So we wanted to look at a way to find these things without, typically they're looked in the 8 micron band or maybe the 24 micron emission where most of them have been found. So anyway, we used a computer-based method to use contour finding and convolutional neural networks to locate these things and search the whole database. So that's basically what we've done. The previous plot showed just our results in the blue boxes. Here I'm just showing, again, our results. And the green are the, just for comparison, the MSX-based survey, which had much lower resolution, so they tended to find much larger regions that maybe weren't actually IRDCs, but maybe just minimum in emission. And then these red objects are the Pareto and Fuller catalog that most people reference when they're looking at IRDCs found by Spitzer. All right, thank you.
It's not progressing. Just keep seeing loading.
Oh, trying to connect.
It seems like it went offline.
Yeah. It looks like the internet's working. Sorry? Jerome? Okay. There we go. Sorry, I'm present.
Great, thank you. All right, hi everybody. My name is Charles Law. I'm a graduate student here at the CFA. And generally, I'm interested in the complex organic chemistry that is associated with high mass star formation. And here I want to talk a bit about some observational work towards G10.6-0.4, which is a known high mass star forming region. And these are new ALMA observations at band 6 at a resolution of about 0.14 arcseconds, or at distance of G10.6 is around 700 AU. And so the image shown right here is the continuum structure of the source. And this is looking at just the densest gas right in the center of G10.6, which is this multi-scale object that has a rotating hot toroid of material. And we're just focusing on the densest gas where we're going to see lots of complex organics. And to give you an idea about the spectral richness of this source, this plot of spectra here is 1/4 of the data that we have, and this is extracting various positions throughout the center of G10.6. And you'll notice you go from regions that are hot core-like, which is this one right here, which basically don't have a continuum. We just see tons of lines at every position we look at, and if we move several thousand AU away, we see regions that are relatively flat spectrally. And so the power of a data set like this is that we were able to go in, choose a representative set of complex organic molecules, and since we have a wealth of molecular transitions here, we're able to fit all of those rotational transitions and basically derive high-resolution maps of the column density and the rotational temperature. So this image right here is for 9 of the complex organics that we looked at, and this is the column density structure. And you can see it varies between the different molecules. And we have a similar image for the rotational temperatures. And by doing this, we notice that there's a range of gas substructure traced by these molecules. And we realize that complex organic chemistry is occurring outside just the hot core region. So this is the hot core right here, but we see a variety of chemistry happening outside of the hot core, and it's not simply confined to the hot core region. And because we were able to do something like this, we can explore correlations between molecules, and that's shown here to the side, and basically look for spatial correspondences between these molecules. And so it's a wealth of data. Come talk to me. I have a poster. There's a lot to explore in a data set like this. Thank you.
Okay, so I'm David Wilner. I'm an astronomer here at the CFA. I've been working on various issues in star and planet formation for a long time, mostly using observations at millimeter and radio wavelengths. And much of my attention for the last few years has been focused on debris disks. These are the very tenuous disks around main sequence stars that result from the collisional grinding of planetesimals, analogous to asteroids and comets in our solar system, left over from the planet formation process. These minor bodies react gravitationally to planets orbiting stars and can persist only in stable regions like belts and resonances. So they provide interesting dynamical tracers of planetary systems. Now, millimeter emission is particularly interesting for these systems because the large grains that dominate the emission at these long wavelengths are more or less unaffected by stellar radiation and stellar winds that kind of rapidly redistribute the small grains that one sees in scattered light in the optical and the visible. And therefore, they share the dynamics of the parent dust-producing planetesimals. So the advent of ALMA has really opened up the ability to image these faint sources, and I just have here on the right side of the slide a few examples. This is the beautiful eccentric ring around the nearby star Fomalhaut, and the reason that it's eccentric is almost certainly due to the fact that there's an unseen planet on an eccentric orbit whose secular perturbations are driving the minor bodies into an ellipse. Up here is an ALMA image of the edge-on debris disk, Beta Pictoris, And what's interesting here is that the vertical structure is resolved into two components. There's a narrow distribution and a broad one. And this is actually just like the classical Kuiper belt in our own solar system, where we think the broad distribution was produced by the outward migration of Neptune that dynamically excited a fraction of the Kuiper belt objects. And here is the debris disk around HR 8799. This one might ring a bell because it's the only directly imaged multiple planet system with 4 giant planets. And if you make the assumption that the outermost planet is what's truncating the inner edge of the debris disk, then that gives you a dynamical estimate of the mass of the outer planet that's independent of its infrared photometry and planetary cooling curves and whatnot, and you can calibrate that. So these are 3 of the now more than 60 debris disks that have been observed and resolved by ALMA, and so there's a lot of interesting applications and things to do. Thanks.
Hi, everyone. I'm Josh Spiegel. I'm also a graduate student here at the CFA, and I work a lot in sort of this interdisciplinary area of astrostatistics. And what I really like to do is try and use computer science statistics and astronomy domain knowledge to really bridge the gap between sort of models, theory, and observations. And more recently, what I've been trying to do is to leverage those skills to actually try and construct sort of 3D maps in the Milky Way. And so, for instance, this work has involved utilizing a number of theoretical stellar models shown on the left, such as the MIST isochrones, which are developed here at Harvard, as well as new sampling techniques to actually explore sort of probabilistically how these things behave with observed data, shown on the bottom left. Then taking those and writing those up into open source packages and algorithms that we can then apply to large data sets, such as DCAPS, an image which is shown in the middle. To then derive robust probabilistic constraints to what we think the distances and reddening and stellar properties are to millions of sources. And then using those in the context of statistical models, actually derive essentially the 3D distribution of dust, gas, and stars, both nearby in the Milky Way and far away. And so on the right here on the top panel is some work that Catherine has led, trying to map distances to local molecular clouds that I'm sure she'll talk about a little later. And on the bottom actually is some new results where we've scaled up lots of our sort of basic technique to try and derive these properties to about 170 million stars at high galactic latitudes. And so in the future, we're hoping to really be able to use this to actually map out the galaxy, both in the halo and in the disk, out to several kiloparsecs to over 2 billion sources. So if you're interested in any of this or just want to talk to me about error bars, just come find me. Thanks.
Hi everybody, my name is Harshil Kamdar. I'm also a graduate student at the CFA. I work with Charlie Conroy. And the broad question that I try to answer in my research is, can we recover disrupting or disrupted star clusters in the Milky Way disk using a combination or either dynamics and chemistry? So the way that we actually approach this question is from a model point of view, from a simulation. So we've built a simulation from the ground up that evolves all stars born in the Milky Way disk in star clusters over the last 5 gigayears. So it has a solar mass resolution. Each star is a particle. But to do this, we fundamentally have to make a lot of assumptions about how to about cluster formation and all that. So all stars in our simulation are actually test particles, because this would be impossible to do in an n-body the right way. So we also have a subgrid model for cluster birth, evolution, and death. We have a realistic potential that includes bars, spiral arms, and GMCs. And we have a semi-empirical chemical model. And we also run control simulations. And on the left, the movie is showing essentially individual points are stars disrupting in different clusters, coded by what cluster they were born in. So it's like ink dissolving in water. It's kind of pretty. And the two results that I want to highlight, and I'm happy to talk about more, are the phase space in the Milky Way disk should be clumpy due to clustered star formation. So this is the plot on the left. It's basically showing the phase space density as a function of the age of the birth cluster and how how much above the mean phase space density in the disk it is. And we also wrote another paper that showed that co-moving pairs of stars, so this is essentially pairs of stars that are very close together spatially, but also in velocity space, are sensitive to both how clustered star formation happens and the large-scale potential of the Milky Way, and that's the plot on the right. So we ran 2 control simulations where we changed the potential and we changed how clustered star formation works, and you can see that it kind of matches up with data in varying degrees. And yeah, so right now we have a pretty simple model for star formation, and I found in the last 2 days star formation is anything but simple. So we're hoping to improve our model, and if you want to improve our models for star formations, if you have any ideas, definitely come find me. Thank you.
I thought maybe we would reshuffle the order. Okay. Yes. So we now go back to research talks, and the next speaker is Shmuel Bialy. Is going to present TurboChem. What can we learn about turbulence in the ISM from observation of chemical tracers? Yeah. You're on the mic. You want the mic? Yeah, I think.
Okay. Okay, meanwhile, you can all wake up, take coffee. Okay, let's see. Maybe the other one. It worked before. Oh, here it is. Okay. Okay, so I'm Shmuel Bialy. I'm from here, from the CFA. Some of you know me. And really, I invented this title because I think it's a nice combination of 2 fields, astrochemistry, different molecules, how they form, and turbulence. So many things depends on turbulence, and it's very important. We talked over this few days how star formation is affected by turbulence. And really, astrochemistry might be a good way for us to learn about turbulence in the ISM. That's what this talk is about. So this is based on 2 papers. We started this when I was a PhD student in Tel Aviv. I was working on the H1 to H2 transition, still in uniform density gas, with my former PhD advisor, Emil Sternberg. Then I met Blakesley Burkhardt, who is doing turbulence. And then we started this investigation. So at first my interest was mostly from the point of view of the H1 to H2 transition, how turbulence affect this. But now I switched, and I'm thinking more of like, how can we use the H1, H2, other molecules to study about turbulence? So I'm becoming more and more interested about turbulence, and this might be a good tool. So this is a recent paper that we continued on this, going to more tracers and to more clouds. So this is based on these 2 papers. So what's the idea? The idea is that in the ISM you have turbulence. We know it from different observations, line width size relations, supersonic line widths, fractal structures of clouds. Turbulence, when supersonic, when the sonic number above 1 becomes compressible and produces density fluctuations in the gas. Now we know that chemistry, the formation of various molecules, is very sensitive to the density. So maybe if we observe the molecules and fluctuations in abundances of various molecules, we can actually reverse the arrows and use this to constrain the density field in the ISM, and so the turbulence in the ISM. So what can we actually learn? So in this talk, I'll mainly concentrate on this route of using the density fluctuations, and two parameters are very important. So for this study is the Mach number and the driving scale of turbulence. And this is related to what can we learn. So what can we learn? The strength of the turbulence in the ISM and the mode. So when I say strength, I mean things like density, things like velocity dispersion, and mode is like if it's solenoidal or compressible. These two things define how much fluctuations do you have in the density field. And then the driving scale, on what scale is the driving acting? Of course, there might be many scales, but basically if it's like on galactic scales, on cloud scales, the scale of turbulence driving will define the scale of the density fluctuations, which then again affects the chemistry. So these are the three main things that I think you can learn from this kind of analysis. So how do we do this? So basically what we do, we run MHD boxes with turbulence. Ideal MHD, 512 cube periodic boxes with driven turbulence. Here is an isothermal equation of state. What we get is something like this, a box with density in each cell. So a 3D box, this is a column density of the box. And then what we do, we now assume that this box is irradiated by UV fluxes and cosmic rays. And now we use PDR modeling, photodissociation region, chemical modeling basically, to model abundances of different molecules in the box. So this, our model include various gas and dust reactions, UV radiation, cosmic rays, based on the PDR model. So basically the radiation propagates inside, and now in each cell you have the abundances of different molecules, and these abundances very strongly, and this is the key here, depend on the density, especially if you pick up the right molecules. Therefore, the abundances that you get will depend on density, so they will depend on the parameters of the turbulence. So in the end, we get these abundances, and we can also go to observations. So sub-millimeter rotational lines of these. Here we concentrated on OH+, H2O+, and argonium H+, which we find good tracers of the density field because they're very sensitive to the density. So we have observations of these species with Herschel, and maybe soon with Sophia. And then we compare the observations with simulation, we can say something about the turbulent field. That's the idea. So for this, we not only run one simulation, we have to run several. So for example, if we run two combinations of driving scales, large and small, and three combinations of Mach number, subsonic, transonic, and supersonic. So we have different turbulence properties. And for each of these boxes, we calculate each of the abundances based on the chemical model. So now we have H, H2, OH2+, H2O+, argonium H+. So we have total of 30 boxes for each turbulent combination and for each species. So we have 30 column density maps, which we can then translate to probability distribution functions, PDFs, and compare this with the observations. So that's the plan. Okay, so let's see some results. I'll start with one example, just the H1, and try to understand what's the effect of these two parameters, the driving scale and the sonic Mach number. Okay, I keep it simple because I want to really, I didn't say, but my strategy, there's different levels of complexity you can take. You can try to be very accurate. I try to be less accurate, but to get some more understanding of what's the effect of each parameter. That's, for example, why we choose isothermal simulations and other many simplifications that we have here. Okay, so let's see what's the effect of the Mach number. So here I show a two-dimensional map projection of the column density of H1 in a simulation with the Mach number of half, so subsonic. So what you see is that there's some variation in the H1 column density between different lines of sight, but the variation is not too large. Why? Because the density fluctuations are not large, they're small, and therefore also the resulting H1 is more or less uniform. However, as you increase the Mach number to supersonic values, then you start to get more density fluctuations, and then for different lines of sight go through different densities, and you get different H1 column densities, and then the PDF also becomes white. That's to be expected. Now, what's the effect of the driving scale? Now, this was for large driving scale. Now, what happened if you decrease the driving scale? If you decrease the driving scale, it means that the fluctuation size, the sizes of these density fluctuations become small. So along each line of sight, you have many, many density fluctuations. And then when you sum over all of them, because that's what you do when you calculate the column density, you get more or less the same answer. You average out all the positive and negative density fluctuations, and therefore you again get a more uniform map compared to the large driving scale. So to summarize this, the PDF dispersion of the column density of H1, and we also find the same trend for other species, not just the H1, all these Argonium H+, OH+ that I mentioned, is becoming wider and wider as you increase the Mach number, because the fluctuation intensity rises, and it becomes larger as you increase the driving scale, because the fluctuations are more coherent along the line of sight. Okay, now let's apply this to observations. I didn't show maps of the, we have all the other species as well, but it's the same idea basically. Okay, so now I want to apply this to observation and see what we find. Now, I show 3 lines, each for a different set of model. The first one is small Mach number. The second is large Mach number and small driving scale. And the third one is large driving scale and large Mach number. Now, these 3 regions, this is 1, 2, 3 sigma regions of the probability distribution function. So this is a joint PDF, but you can ignore this and just look at the x-axis. And the point are observations using Herschel of these species, Argonium H+, OH+, and H2O+. And what you can see is that the spread in the species is quite large. So with a model of small Mach number, you get a much smaller PDF compared to what you get from observations. As you increase the Mach number, the PDFs becomes wider, but not wide enough. And finally, only when you also assume that the Mach number and the driving scale are large, only then you can reproduce somewhat the observations, the spread and the dispersion and the column densities. So that's the third model. So naively, you'd say, comparing the model with observations, you would conclude that both the Mach number and the driving scale in the ISM are large. So we can constrain turbulent parameters with chemical tracers, but. So there are several caveats, or we're in the US, so I would say future prospect. Okay. So first of all, here I did assume a chemical equilibrium. In fact, when in a turbulent box, where you have these turbulent motions, if the time scale for turbulent crossover time becomes short compared to the chemical time, then the assumption of chemical equilibrium might be not valid. And then you should follow the time-dependent chemistry. So this is, so I was making a joke, but this is really future prospects. So this is some things that I want to work now in the future. Then non-isothermal. Here the simulations are isothermal, but actually non-isothermality may become important because you can have warm neutral medium, cold neutral medium, and depending on scale, if the scale of the cold neutral medium is small compared to the radiation sources, then you can have the warm neutral medium also affecting the abundances. So this may be important. Then fluctuation in other quantities. So there are other things that can make fluctuations in the chemical tracers apart from turbulence. For example, if the cosmic ray ionization rate changes between different locations, you would also expect the abundances to change. And I just make a short note on this. So, and to advertise my recent paper on arXiv, comments welcome. It's still in the review process. So the problem is that how do we learn about the cosmic ionization rate? We usually use these same tracers that I just talked about, argonium H+, OH+, H2O+, H3+, different abundances like this, with chemical models, the same chemical models I use, or some other variation of this, to constrain the cosmic ionization rate. So actually the problem is degenerate. We don't know if it's the turbulence with density fluctuations that makes the fluctuations in the chemical abundances, or if it's fluctuations in the cosmic ionization rate. So we need some other method to constrain the cosmic ionization rate. And here I suggested that infrared lines of molecular hydrogen, if detected, can be used to constrain the cosmic ionization rate. I don't have time to talk about this, but talk to me later. And finally, I just conclude that if all this is checked with V, then we can use observations of chemical tracers to constrain turbulent parameters. Thank you.
Okay, we have 1 minute for questions.
Yes. Okay, this idea is very nice, but can you give us more details about the comparison with the observations? Because in all your boxes, you're always scale-free, but then when we compare to real life, we have to put down coordinates.
Right.
And whatever data points were in your one of the last plots, they must have been measured by doing PDFs on certain physical scales across certain columns.
Yeah, so that's
how this.
It's true. In the MHD boxes that are scale-free, so we have to assume something. So in the model, there are quite many free parameters. One is, as I said, cosmic ionization rate, UV, things like this, and the other one is what's the actual size of the box. So we assumed some size. We assumed six parsecs, right? Some AV based on some suggestions. But this is, you can think of it as another free parameter. What's the size of the box? Then there's another complication that in the observations, this is an absorption. You go through the galaxy and you have many, many clouds along this. So actually we took the PDFs that I show first and we stacked them together to get a grand, what I call grand PDF of this many clouds along the line of sight. So yeah, there are many, many complications. That's why there are future prospects.
Simon?
Yeah, so you say the width of the constrains the Mach number, but actually we know it constrains the product of the Mach number and the plasma beta parameter.
Right.
So
and also the B solenoidal to
so,
compression.
Is there any way to break that degeneracy, or do you actually just get that combination?
No, so when I said Mach number, I actually meant this multiplication, BMS, not Mach number. But yeah, it's a good question. I have no immediate answer.
Okay, thank you.
Thank you.
So the next speaker is Manuel Riener. Is going to talk about the detailed velocity structure and distribution of CO emission in the galactic plane.
Okay. Yeah. Sorry. Okay, perfect. Thank you very much. First of all, thanks also to the organizers for giving me this opportunity to talk about my PhD project, and also thank you very much to Kara for giving this nice introduction to my topic already. Because I fully agree with you, we're living in the golden era of galactic plane surveys. Now let me show this on this schematic overview of our Milky Way. So these are just galactic plane surveys from the last 10 to 15 years that also targeted one of the three lowest rotational transitions of CO. And each one of those galactic plane surveys has like a spatial resolution better than an arc minute, and a spectral resolution good enough to resolve the thermal line width. Now this is a massive amount of data, and we got the entire galactic disk covered in this one single isotopolog. there's obviously many things we can do, and the questions I'm most interested in are, we want to follow the gas flow from galactic to subcloud scales, and we want to characterize the detailed velocity distribution. We're also very interested in generally the distribution of 13CO in our Milky Way, and we want to make synergies with different ISM traces, for example, dust emission. Now, and to answer each of those questions, we really have to deal with the complexity of one of those galactic plane surveys and reduce its complexity, actually. So in my PhD project, I was focused on the galactic ring survey. So most of you will know this survey, and Kara also introduced it already. So it covers a very interesting fraction of the inner galactic plane. It's a 13CO survey, and it encompasses about 2.4 million spectra. And especially in the inner galactic plane, it can get very messy and complex. To deal with this enormous data set, I developed a Gaussian decomposition algorithm called GaussPy+. So it is based on a pre-existing algorithm that is called GaussPy. I won't go into any technical details. It just GaussPy fits spectra, emission line spectra, in a fully automated way. And we added some additional capabilities to also extend its fitting functionality to low signal to noise regions, and have like automated quality checks, and maybe most importantly, we have a spatially coherent refitting routine. Now, just to show you some of the results we obtained. So this is the galactic ring survey, the original data set, the zeroth moment map, so integrated along the whole velocity range from the inner galactic plane to the outskirts here. And this is the same map, but this time recreated from our Gaussian fit components. And if I switch back and forth, you see we really do, I think, a good job in retaining all the flux and recreating this data set. This is also shown in this video here, where I basically go through the velocity channels. In the upper channel, you see the original data set, and in the lower panel, you see here the data set again recreated from our fit components. And you see we can actually recreate all the fidelity of the data set, by at the same time massively reducing its complexity, because we describe it just with the Gaussian fit parameters. And obviously there's many things we can do now having this Gaussian fit parameters in hand, but I just want to tell you what we actually did. We focused a bit more on the global parameters of the gas emission. So first of all, we were very interested in the complexity. Can we describe the complexity along the line of sight in the spectra? What you see here is a map that shows you the number of fit components we used per spectrum. And you can see here, especially in the inner galactic plane, we needed up to 10 or 12 fit components, which means there were 10 or 12 emission peaks along the line of sight. And what I'm going to show you now is like a comparison where on the one hand, I want to compare the number of fit components as a measure of the complexity of the spectra with the integrated intensity that you've already seen. So I take like different subsets. What I do here is like I focus on all the spectra where we fitted no CO components, look at the corresponding integrated intensity values, and construct a probability density function here. I do the same thing for all the spectra where I fitted one component, two components, and so forth. And I really populate this rich plot here with these probability density functions. And what this shows you here is that if we measure high integrated intensity values for our spectra, they are more likely to be connected to more complex spectra, to more fit components in this case, but more structures along the line of sight. So you see here really a clear trend. And that might not be that surprising, or might be what we would expect, but we can play a similar game where just correlate this measure for complexity from the CO spectra, but this time with like H2 surface density that we inferred from dust emission, in this case the Heidelberg survey. And you see a very similar trend that also for the dust emission, where it's not very clear, how you measure the complexity along the line of sight, but it seems also to be the case that, higher H2 surface density, as we infer from dust emission, is correlated to more complexity as we measure it from the CO. So in the next part of my talk, I want to go away from complexity and talk about confusion along the line of sight. What I showed you so far was like really an integration along the whole velocity axis, but we can restrict this to a narrower velocity range. So here it shows velocities that are very close to the local standard of rest, so -5 to 20 kilometers per second. And the emission that you see in these panels actually comes from fundamentally different places in our galaxy. Now let me illustrate this. So what you see here is like a cartoon overview with the sun here, galactic center here, and this orange wedge shows you the coverage of the galactic ring survey. What overplot here are like constant projected VLSR curves. That means like the emission that I showed you before either comes from very close by or very far away in the disk. And if we take any random line of sight in the inner galactic plane and we have a peak at a certain VLSR value, it will always correspond to two positions in the galactic plane, in the galactic disk. And especially far away, this could correspond to emission from the Perseus or outer arm. Now, if we think about a structure embedded either nearby or far away, and the structure has like a clear velocity gradient, if we detect it nearby, we are able to spatially resolve it well, and we measure a fairly narrow line width, whereas far away, we will average the structure in a beam, and we will get a much broader line. Now, I will now illustrate how this can help us to actually disentangle the emission that we see here. So if I now go from this emission map, and in the next map I show you from our fit components, the narrowest velocity dispersion that we have in this restricted velocity regime. So even if we have multiple fit components, I only focus on the narrowest one. And you can see immediately this, the low velocity dispersion values, the bluest ones, you see them all over the place in galactic latitude. But the high velocity dispersion values, if I make a cut at 1 kilometers per second, you see they are much more concentrated. So if I take just a simple fit through that, and overplot also what the full wave half maximum extent of the gas disk would be at around 8 kiloparsec from the sun, you see actually a fairly good correspondence. And also if I will plot here the inferred positions of the Perseus and outer arm. So we really think this our fit components could be useful as a prior to disentangle this confusion. And moreover, we think that especially in this velocity regime, if we measure high velocity dispersion values, those are not due to mostly not due to high non-thermal motions of close by regions, but rather due to beam averaging effects. Now I want to go and show you another transformation we can do with our Gaussian decompositions in hand. So what I did so far was still, we recreated the data set, but I still showed you the entire integrated emission. But we can go one step further and look at the integrated emission per fit component, and in an additional step, concentrate this integrated emission at the centroid position. So we get rid of this blurring effect from the line width. I illustrate this in a position velocity view. So here you see galactic longitude versus velocity again of the entire galactic ring survey. So this would be the classic position velocity view, and you see it's very washed out due to the effects of the line width. But if I now make this transformation, you can immediately see how the velocity structure appears really. It's especially striking in those smaller panels where I show like giant molecular filaments that are actually located on fairly different regions in the galaxies probed by the GIS. But still, this is integrated over the whole galactic latitude range. So there's still a lot of stuff that I'm integrating over. In the next video, I show you instead when I take slices of galactic latitude and move here along galactic latitude, how this velocity distribution actually changes. And you see there's a lot of complexity in here. So, what it means, we're currently actually working on it, in interpreting it. And this is an effort that's led by Johnny Henshaw from the MPIA. So we see similar velocity fluctuations in entirely different data sets on entirely different scales and environments. And we get some ideas how to interpret them, but you will soon hear much more about this. So in the last part of my talk, I want to focus on the distribution of the 13CO in our galaxy. And again, in this position velocity view, if I just overplot like spiral arm positions, you can see that it's very difficult to actually disentangle and like find out which emission is part of which spiral arm. So what we need is really distances, and in an ongoing project that I'm currently working on, we want to use Mark Reed's Bayesian distance calculator tool to infer distances to all our 4.5 million fit components of the galactic ring survey. So this Bayesian distance calculator tool, it uses different priors. I won't go into too many details, but I just show you here some results from a test run. So this is like the outcome with the default settings of just when I plug in all my PPV data points from the Gaussian decomposition into the Bayesian distance calculator tool. And in this view, you can see really in the default settings that the prior that we gave it for the spiral arm information has like really a strong effect. So the emission is really heavily biased towards spiral arms. But the nice thing is with Mark Reed's tool is you can deselect priors or give them different weightings. And in this case, I completely neglected the spiral arms, and you can see it's much more dominated by kinematic distance ambiguities and its uncertainties. And we think we can use those different runs to find like fractions, upper and lower limits for the gas emission in spiral arm and interarm regions. So this is basically what I have done so far on my work with the GIS. And in the near future, we plan to actually extend this to the entire inner galaxy with a very big survey, the SEDIGISM survey that covers almost the entire fourth quadrant. And in the also near future, we want to correlate this with a new dust extinction map that's coming up very soon from my supervisor, Joni Kainulainen. But with this, I want to leave you with my summary, and thank you for your attention.
Questions for Manuel? Okay, I'll start with a question. So when you try to distinguish between whether it's close by or far away, what is the significance of the velocity dispersion that you observe?
Yes, you're talking about with what's the confidence that I place
Yeah, or with numbers, what are
it's
the
like we
values
just,
that you observe?
in this case, we use like a simple size line width relationship. So from Solomon et al. To gauge like what would be our beam, what would be the expected line width given our beam at the far distance, and this we use as a cutoff. So this is of course not like an entirely precise method, so there will for sure be like more turbulent regions close by, I don't doubt that. But I think like on average this could be a good prior to disentangle the bulk of it. Yeah.
Thank you. Yeah.
I'm really impressed by your kinematic distance ambiguity resolution. Have you also compared it to results from, say, H1 admission absorption experiments to resolve those distances?
Not yet, but that's definitely the plan to now test how well this actually works. Yeah.
I just wanted to ask a little bit about the decomposition package. So those results look phenomenal. They look awesome.
Thank you.
So I'm just wondering, we also had like Scouse, and then I know there's like a convolutional neural network code that also does some decomposition. Is like Gauss pi plus, is that the thing now? Is that what we're on?
Say yes.
No, I say it entirely depends. So this, with Gauss pi plus, we had a heavy focus on like big service, on big emission line service. So Scouse, for example, is the perfect tool if you study on individual regions where you don't expect that much complexity that also changes that quickly, because you still have this semi-automated step that you have to go through. So I think almost any of those tools are a good step forward, and better than to use like moment maps. I think that's actually the step we have to take. So yeah, our focus was more like really to have like this fully automated way for this big emission line service.
Okay, if there are no further questions, let's thank Manuel again. So the last speaker for today is Catherine Zucker, and she's going to talk about the galactic scale gas wave in the solar neighborhoods.